You've probably heard exploration versus exploitation explained like it's a simple personality choice. Be adventurous or play it safe. But reinforcement learning doesn't get to treat it like a vibe. Exploration can be expensive, confusing, and sometimes actively punished by the environment. And in the real world, robotics, finance, recommendation systems, bad exploration isn't just suboptimal, it can be dangerous. In this fifth part of the series, we're going to dig into why exploration is hard, then build up from the classic epsilon-greedy trick to softmax and entropy bonuses, and finally to uncertainty-driven exploration, UCB and Thompson style ideas that try to explore with a reason, not just randomness. Let's start with a truth that's easy to ignore. The agent doesn't know what it doesn't know. It's not a human looking at a map with the unexplored regions shaded gray. It's more like someone waking up in a new city with amnesia and only learning by walking into streets and seeing what happens. Exploration hurts because you pay for information with time and reward. Every time you try something new, you're giving up the action that currently seems best. That trade-off is the core tension. But what makes it really nasty is that the cost of exploration is immediate, while the benefit might arrive much later. In many tasks, the environment doesn't give you helpful feedback often. You can do 1,000 actions and get nothing. Think about a platformer game where the only reward is level complete, or a robot that only gets a reward when it successfully picks up an object. No points for getting close, no points for trying. In sparse reward settings, naive exploration can be brutal. If you're mostly acting randomly, you're basically hoping to stumble into success by accident. That can work in tiny toy environments, but as the space grows, pure luck becomes a terrible plan. And here's the psychological twist. From the agent's perspective, the world looks the same, whether it's doing the right thing but hasn't gotten there yet, or doing the wrong thing forever. Both situations produce the same signal: nothing. Sometimes the environment gives you rewards early, but they're misleading. You find a little strategy that works okay, and it starts paying reliably. Your agent learns, this is safe. The problem is that safe doesn't mean optimal. This is why exploration is not only about finding reward, but also about refusing to settle too early. An agent can become addicted to a small reward loop. In games, this might look like collecting easy coins instead of learning the harder route to the big objective. In product recommendations, it might look like showing users the same type of content that gets quick clicks, even though other content could lead to higher long-term satisfaction. Deceptive reward is the comfort trap. And exploration is hard because it asks you to be uncomfortable on purpose. Even when rewards exist, they often arrive late. The agent might take 200 steps and then get a reward. Which of those 200 steps mattered? The agent has to figure out how to assign credit. This makes exploration harder because the feedback loop is stretched. You can't just try one action and instantly see if it was a good idea. You try a whole trajectory of actions, and the reward at the end is like a cryptic message. Some part of what you did was helpful. Good luck figuring out which part. When credit assignment is hard, exploration gets noisier, because even successful exploration doesn't clearly teach you what to repeat. Here's a key idea that will matter later. It's not enough to know what action has the highest estimated value. You also want to know how confident you are. A big chunk of bad exploration happens because the agent becomes confident too quickly. In deep RL, neural networks can output sharp preferences even when they're basically guessing. That creates premature exploitation. The agent stops exploring not because it solved the problem, but because it feels solved. And that's a perfect transition to our first exploration method. Epsilon-greedy is the classic baseline for a reason. It's extremely easy to implement and surprisingly effective in many settings. The policy is basically, most of the time, choose the action you currently believe is best, but sometimes, epsilon% of the time, do something random. That little bit of randomness keeps the agent from locking into one behavior too early. It's like telling the agent, look, I know you're feeling confident, but take a few curiosity bites anyway. Epsilon greedy works because it guarantees that every action gets tried eventually, at least in a small discrete action space. If there's an action that's secretly amazing, Epsilon greedy has a chance to discover it, but it feels dumb because the exploration is blind. When Epsilon triggers, the agent does not choose a smart alternative. It chooses a random action, including actions that are obviously terrible. In a simple bandit problem with 10 actions, that might be fine. In a real controlled task with continuous actions or huge action spaces, random actions can be meaningless or even catastrophic. One of the most practical improvements is to change epsilon over time. Early training, you want more randomness because you know nothing. Later, you want less randomness because you're trying to refine. So many implementations use epsilon decay, start exploratory, then become increasingly greedy. This creates a training narrative. First you roam, then you commit. But even with a good schedule, epsilon greedy doesn't solve the blindness problem. It doesn't explore what matters. It explores whatever randomness hits. So now we move to methods that turn exploration into a weighted preference rather than a random switch. Softmax exploration says, instead of choosing the best action almost always, choose actions with probabilities based on their estimated values. So if action A looks best, it will still be chosen most of the time. But action B, which looks slightly worse, will still get selected occasionally, and actions that look awful get selected rarely. This is a big conceptual shift. Epsilon greedy treats exploration as a separate mode. Now I'm exploring. Softmax bakes exploration into every decision. Softmax comes with a temperature parameter. High temperature means the agent is more random. Low temperature means the agent becomes more deterministic. Early training, a higher temperature encourages wide exploration. Later, lowering temperature helps the agent settle into the best behavior it has found. Softmax can be smoother than epsilon greedy and often feels more reasonable. But it still depends heavily on value estimates. If the value estimates are wrong, softmax confidently samples from the wrong distribution. That leads to a more modern tool, encouraging exploration directly inside the learning objective. In policy gradient methods, you often have a policy that outputs a probability distribution over actions. That gives you something you can measure: how spread out the policy is. Entropy is a measure of randomness or diversity in that distribution. If the policy always picks the same action, entropy is low. If it spreads probability across many actions, entropy is high. An entropy bonus literally pays the agent during training for being uncertain and trying multiple actions. Without entropy, policy methods can collapse too early. They find a strategy that works a little, and the policy distribution narrows quickly. Once that happens, the agent stops collecting new experiences and learning slows down. With an entropy bonus, you're basically telling the agent, don't become a one-trick pony yet. You're buying more exploration time, but entropy is still not directed exploration. It spreads actions, but it doesn't ask, where would learning be most valuable? To do that, we need uncertainty-driven exploration. Here's the dream. Instead of exploring randomly, explore strategically. Go where you're uncertain because uncertainty is a signal that new information is available. This is where UCB and Thompson style ideas live. They're especially famous in bandits, but the intuition generalizes. You want a mechanism that naturally explores uncertain actions and naturally exploits confident winners. Upper confidence-bound methods pick actions based on an optimistic score. Conceptually, it's like saying, I'll assume each action is as good as it plausibly could be, given what I know. So the score isn't just the estimated value, it's the estimated value plus a bonus for uncertainty. Actions you haven't tried much have bigger uncertainty, so they get a bigger bonus, so they get explored. And as you sample an action more, uncertainty shrinks, the bonus decreases, and the action stops being artificially attractive. Exploration fades naturally. That's a huge upgrade over epsilon-greedy because it replaces blind randomness with curiosity that has a purpose. Thompson sampling is a different flavor. Instead of adding a bonus, you sample a plausible belief about the world, then act greedily in that sampled world. Think of it like role-playing alternate realities. In one reality, action B might secretly be the best. In another, action A might dominate. If you're uncertain, you'll sample different realities over time, and that will cause you to try different actions. As you learn more, your belief distribution tightens. Your sampled realities start looking similar, and your behavior becomes consistent. Again, exploration fades naturally. In deep RL, the challenge is that standard neural networks don't give calibrated uncertainty by default. They can be wildly confident in regions they've never seen. That's why modern uncertainty-driven exploration often uses extra techniques like ensembles, randomized value functions, Bayesian-ish approximations, or distributions over value estimates. Even if you don't implement those today, the mindset is important. Good exploration isn't about being random. It's about being uncertain in the right places. Here's the practical summary, framed as how these feel during training. Epsilon-greedy is the blunt instrument. It's reliable and easy, and it's still used as a baseline everywhere. If you're learning RL, start here because it teaches you the core trade-off with minimal complexity. Softmax and entropy bonuses are smoother. They reduce the now I'm exploring switch and instead create a controlled spread of behavior. They often behave better in policy-based methods, and entropy in particular has become a standard ingredient in many modern algorithms. Uncertainty-driven exploration is the strategic version. It asks for more machinery, but it aligns with what you would want an intelligent learner to do. Test the things you're unsure about, because that's where information lives. And now we're at a cliffhanger that's honestly one of the most exciting parts of exploration in RL. Because once you accept that uncertainty can guide exploration, the next question becomes, what if the agent could generate its own reasons to explore? What if novelty itself felt rewarding? What if learning progress became the signal? In the next part, we'll talk about intrinsic motivation, curiosity-driven exploration, novelty bonuses, and why curiosity can be both a superpower and a trap.